Hello, welcome to Greed, Lies, and Deceit, Curious Stories of Player Misbehavior. My name is Frank Paolino. I'm from Akamai Technologies. I come to you on behalf of the Client Optimization Program. At Akamai, we are continually evaluating our own performance and continually optimizing. However, we thought we'd turn some of the focus onto the client side of the equation. And with that, a team of sleuths at Akamai have been tasked with uncovering anomalous or unexpected behaviors and how video players and or clients are interacting with the CDN. They have access to a fantastic global data set in which to look for clues and gather evidence. And that is, of course, millions or billions of CDN log lines. These log lines represent access from the most popular OTT video services. And those requests, of course, are made from the most popular video platforms. So to look at the data in this way, we did need to develop a new tool, and we developed a new internal tool called GOLO for short, stands for Ghost Log Analysis. And here's how GOLO works. Of course, we collect the logs on the Akamai servers from all the client requests. Those logs then are available to the GOLO tool, and the GOLO tool pulls those logs and pre-generates a number, hundreds of graphs, reports, and tables from which we can detect anomalies. The output of the GOLO tool gives you output in terms of requests broken down and sliced and diced by a device or user agent, but it also approximates sessions within that data set as well and breaks down those sessions statistically across a number of metrics by user agent or device as well. And there's even the ability to zoom in to the per session as if you had a Charles capture to look at the request pattern within individual sessions, which is very powerful. Together, this ability to zoom in and zoom out of the data set in this fashion does provide a method to surface both player and CDN opportunities for improvement. Now, to set a baseline about the player's job, we all know players have a tough job, and for the most part, they're doing great. OTT video growth is exploding. The cord is being cut, and in the last 12 months, we've seen every major strategic OTT service launch. Players, as we know, are downstream. They're subject to the content they are processing, the local resource availability of the device, and then the input from the end user. They have to fetch, buffer, unpackage, decode, and render. However, in the CDN, in the player to CDN interaction focus, we're going to really more focus on the fetch side of things. So let's look at some basic fetch patterns to set that baseline. I'm going to go through a little bit of an illustration of how we may illustrate some of these anomalies in the presentation. On the left, we have player. On the right, we have CDN. But we're going to actually sequence the request from the player going from left to right in some of our diagrams. So a dotted line is connection, video segment request as follows, and the musical notes for the audio segment. So here is the first common pattern we see in players, right? They fetch on a single connection with video segment requests, audio segment requests. The player creates a connection with CDN, holds onto it, and puts all the requests on the connection and does them in a pretty serial fashion. This is seen on a lot of players. It's also seen on some of the popular OTT players in some of their modes on Roku and Exoplayer. A second popular approach is the connection pool approach, right? We have a number of connections established between the player and the CDN, and then the requests are then round robin on that or distributed some other pattern where the video, audio, and manifest requests or even caption fragment requests are made on that connection pool. This is a very common pattern you see on Exoplayer and also on AV Player as well. Thirdly, we have a more creative, you might see in some players, a more creative approach as follows, where the actual video segments are broken down into smaller range requests that are issued then in parallel over a parallel set of connections between the player and CDN. This approach is actually an approach we see commonly on Roku, and it's pretty creative, and we have seen in many sessions Roku switch into this mode when it thinks it's going to be a more valuable approach. So with these three examples of fetching scenarios behind us, let's dive into some of the anomalies we have found. So we'll get started and we'll go to the first, which has to do with the lack of connection reuse. So in our data set, one of the things we noticed across several of our OTT analyses was that the Sony console appeared to not be reusing connections. So let's take a look at how this surfaced. The table on the top here is user agents in each row, or summarized consolidated user agents, and then a frequency of request numbers in the body. and it's done with a percentile display. So in 1.143 million requests for this particular data set we had pulled, the request number out of all the request lines was always 1 for the Sony console, for the PS4. Other Microsoft console was spread out, Exoplayer, and all other devices. It's more common, of course, if there's 200 requests, to see much higher numbers spread out across all of those requests. Now, if we zoom into a particular session to validate that, here's a graph before of a specific individual session validation from that data set, where we have request number on the y-axis and time on the x. And so each one of these red dots represents a request, an object request. And as you can see, every time the Akamai logline entry is showing that it was request number 1, meaning the first request on a connection to the server. So illustrating this in a simpler fashion, we can see, connection is opened, a video object is retrieved, and then the connection is closed. A new connection is opened, video object retrieved, connection is closed, etc. So we noticed this across PS4 video apps, and we then asked ourselves, well, is this native? Is this a platform limitation? Now, when we look at PS4 game downloads, we definitely don't see a lack of connection reuse. And also, we had one of the OTT providers we studied had terrific connection reuse in their video app. So our suspicion is that there's a number, there are a number of player building approaches and frameworks on the PS4, and it just could be that one of the underlying libraries default is to not reuse connections, and maybe it's buried somewhere, and application developers have not chosen to alter that setting or utilize that API. We're actually talking to Sony engineering as we speak, so we can hope to surface that we and they can surface the information to our, to the app developers out there. Now, on another platform that is commonly using reconnections, we saw some cases where it wasn't. Here's, an iOS device where on the top graph, it's plotted request number. This is the pattern you like to see. These are 2 lines moving up and to the right, connection reestablished. So essentially it's 2 parallel connections, request number always moving up, showing really valid, really proper connection reuse. On the bottom though, we see some sessions that look like this on iPhone also. And that is requests going from left to right, request number plot. And we see everything's on connection on request number 1 for the connection. Some go above that, and then we see maybe a new piece of content's being played and it breaks out of that pattern for a little bit. But overall, we see a pretty flat pattern. So that is something we just wanted to note, that while iOS, tvOS will most often reuse connections properly, there's some percentage of cases, and we're not sure what that percentage is. Is it something like, maybe something under 5 or 10%, but it's something we did see across a number of analyses. So it's not unique to one publisher. And of course, we know AV Player is a well-oiled machine, and it's used, as the player for all the apps across Apple devices. So the lack of connection reuse, the impact of that, of course, is going to be that there's more overhead, in the overall process, to TCP connection establishment, the TLS negotiation for every object, and that will lead to lower peak throughput, higher time to first byte, potentially lower average bitrate plays, increased rebuffering, lower QoE. For publishers, with PS4 applications, we think they should take a look to be able to enable the appropriate settings to enable that TCP connection reuse. And as we find out more information, we'll bring that forward as well. So let's look at a second scenario, a second anomaly or unexpected behavior we identified. And that has to do with Xbox and DNS-TTL. And so first, again, I want to show you the graphs of how we surfaced this. One of our graphs, and this is a session-based graph rather than a request-based table, whereas we looked at all the sessions, for all of these user agents, and this is only a portion of the table, and the Microsoft console showed that it was only accessing 1 edge server, and this plot kind of shows how many edge servers the sessions were accessing. So, if we look across something like Apple Desktop, we saw 82%. Accessing 1 edge server, 50% accessing 2, 2% accessing 3. It's pretty, that's a pretty common pattern, but in some sessions we see anywhere from 1 to 5 to 10, depending on length of session, depending on the number of connections established. It can vary quite a bit, but consistently across a number of OTT providers, their Xbox application or studying their Xbox traffic on those OTT services, we commonly saw only 1 edge server being accessed and having a 99 or 100% fall in this one column. Now, if we zoom into an individual session on the right here, you can see the same thing. This is a plot we have that's an individual session plot, time from left to right, and then the edge machine index. 0 is the first edge server, 1 would be the second edge server, etc. But you can see in this plot, everything's on the 0th edge server, meaning only one edge machine was accessed. So illustrated in a simpler way, most players, accessing a number of edge machines, even as they reestablish, close and open new connections. But on Xbox, we're seeing essentially always one edge server being accessed. And even again, as new connections are open and closed, it has a high affinity to a single edge server during that session. Now, the impact of sticking to a single CDN server would just be that there may be suboptimal performance. Akamai as a CDN and other CDNs who have a similar approach may continually kind of adjust load, and they expect this could happen within a minute, within 2 minutes. That if a server is getting overloaded, traffic, your next connection may happen to another server and may spread the traffic out. And so, for longer running sessions to be stuck to one session, there's a chance that you could end up with some suboptimal performance if that server becomes overloaded. So we think a good solution is to honor the DNS cache, TTL, and then re-resolve, of course, upon expiration. Okay, so let's look now at a third unexpected behavior. This has to do with the multi-CDN scenario that a particular publisher was using. So here again, looking at our graphs from our Golo tool, again, we're starting with a request number plot, but this time we get to look at some log lines below where we zoom right into log lines. But here's a request number plot. We're seeing a little bit of connection use up here, but then we see, connection number one, all throughout, and these groups of 3 requests at a time. And this chart may be over a slightly longer time period over the others. And then if we look below here, we have the log lines, and we masked, of course, the full path here, but you see the end of the path. So we see segment 97, 98, then 100, 101, 102, then 104, 105, 106. So it appears that every 4th segment is not being requested from Akamai, but from another CDN. So we checked with the setup, checked with our Akamai account team, said, yes, that is indeed the multi-CDN setup this customer approach they're using in this scenario. And what's interesting is if you look a little further, the first segment after the skip segment has a little P here, and that little P indicates that the edge server had to go to parent to retrieve it, to fulfill the client request. So essentially, the segment wasn't able to be kind of essentially pre-warmed at the edge server by an optimization we have called edge prefetching. And so it wound up being that 40% of client requests wound up having still to go to a parent. And our setup for that customer and the customer's configuration, their delivery configuration, was such that edge prefetching would be enabled, and this would not be the case. So essentially, this particular multi-CDN setup of sending the 4th segment to another CDN is actually diluting the impact of the intended optimization for the Akamai CDN here. So we can see that illustrated up above here: 1, 2, 3 from 1, 5, 6, 7, 9, 10, 11, and that segments 4 and 8 going to another CDN. Now the impact of this is that Akamai's edge prefetching impact then is going to be limited. It's not going to be achieving its full goals. Colder hits, higher time to first byte, lower throughput, lower QE than otherwise if the optimization was fully in place. In session CDN switching, of course, ideally should be performed only if there's with this kind of setup, if there's a performance regression with Akamai or with the CDN, or at least otherwise tune accordingly. Like plan the CDN switching approach in conjunction with the CDN specific optimizations that are being implemented on your CDNs. That's, I think, the lesson here. So finally, a fourth finding and anomaly has to do with Apple TV Trick Play Burst. So we all know about Trick Play. I think Trick Play are these iframes, and the various names for them. Are these images that are hover preview on web players or seek preview on this Apple TV. Sometimes they can be used as full frame on different devices, but here we're talking about those preview images that allow a really smooth and informative seeking experience. So here we have, on this case, we're actually showing the same session on both graphs, but they're different graphs. First, on the top graph, we have a session that is showing this graphing status code, and then we have that same individual session with the parallel graph showing request number. So first, let's take a look at status code. We can see every about 5 seconds a request that returns a 200 response code. And then up above, we see a flurry of requests between those 200 requests that are they're returning a 206 status code, which is a successful range request response. And so ultimately what we're looking at here is, the 206s are the range requests for the trick play images. Apparently when Apple TV starts up a VOD session, it's going to go ahead and retrieve all of those images. And we'll see during the first 10, 20, 30 seconds of playback, a retrieval of all of the preview images that are needed for that playback session so that we can have a smooth seeking experience in the UI for the end user. If we look now at the parallel graph down below where we have request number plotted, well, we see these 4 lines, they're bunched up together here, but they spread out. So we have 4 parallel connections established for those trick play image requests. And we have another connection that is actually retrieving the video or the video plus audio segments. In quite a nifty way, AV Player is actually pausing the retrieval of the trick play images while it's actually downloading the video segments. And that, of course, would be presumably not to compete for bandwidth and have the player think it has less bandwidth than it does and downshift to a lower rendition. So this is a pretty cool, pretty aggressive, but a pretty cool approach. So the simpler illustration of that, as we see here, range requests represented by the little images, and then, of course, the video segments by the little film strips. And the lack of competition that these all stop while the video segment is being retrieved. And of course, this stops after 10 or 20 seconds once those trick play images are all retrieved. Now, when we look a little bit more into trick play, I mean, of course, there's an iframe playlist in HLS, and that is, those playlists, point to where the iframe, or the trick play images are located. And there's, here's an example of 3 different ways that could be set up. One is that those iframes are embedded within the regular video segments. So here we have, kind of segment 1, it's got iframes, it's got the video in the yellow, but it's also got the iframes, in the green. And then also, you could also just put a collection of iframes in their own playlist, in their own files, their own segment files. You could also put all your trick play into its own files for the entire piece of content. And that's an approach we've heard from customers as a simplification as well. But very often, though, that default setting that's on the left here is what's going to happen by default with many customer setups. And so here's the example of what the unintended side effects can be of that. You can have, the client is requesting a 50K image, but then depending on the CDN tuning and setup, depending on the partial object caching rules and things like that, we can have this edge server have to request a 1.5 megabyte segment from one tier of caching, from the next tier of caching, and ultimately from the origin. So when the client needed 50K, it went ahead and got 1.5, and then imagine multiplying that out. Now, if we look, we analyze a specific session, and down below shows the results of that, and let's look at that. If there's only 0.03 gigs needed for the trick play traffic in a particular session, that can actually balloon out to, that 30 megabytes can balloon out to about 400 megabytes request all the way back to the origin. And then also, so that's causing a lot of extra migress within the CDN, and it's also causing a lot of extra potentially load on the origin as well. So in one particular scenario, we actually saw an amplification effect of up to 80 megabits per second on the origin from such a request. So really, this can have some this aggressive, nifty yet aggressive approach of this bursty retrieval, coupled with how this is done on the how the iframes themselves are stored in the video segments, can cause some unintended side effects in the delivery chain. So, trick play burst with its default range request in the video segments might unintentionally amplify, have that amplification effect for both within the CDN and the origin. So we'd recommend to just keep this in mind and consider a workflow for trick play that maybe where it separates the trick play content separate from the video, just to really decouple those things. And that should be easy to do during the coding process. But this is an opportunity where you can have client, video, workflow, and CDN just all working together. So here we've looked at 4 different scenarios of unexpected behavior that we have uncovered through our study of our CDN logs, but through the client lens. We had the PS4's lack of connection reuse, potentially impacting QoE. We had Xbox seeming to ignore the DNS TTL, stick to one edge server. We saw that a multi-CDN scenario by a customer with all good intentions was accidentally diluting their CDN-specific optimization. We also saw that Apple TV's nifty trick play burst was aggressive and pretty cool, but can have some unintended consequences in that delivery chain. So are players greedy? Are they lying? Are they deceitful? Well, they're all trying to do the best they can. They're doing a lot of great things, so I would say no, but definitely there are opportunities to improve. And with that, I'd like to just leave a couple additional thoughts, which is we entered this analysis looking really to focus on the player to CDN interaction, and that's where our focus was. But as you can see with a couple of the items there, we really found that you had to think a little bit more about things beyond just those parts of the workflow. That we look a little bit more at the CDN switching, look a little bit more about the content preparation. So we think there's a good opportunity for player builders, publishers, CDNs, just to remember to continue to work together, to think about the end-to-end setup, and to ultimately deliver the best quality of experience and the most efficiency. And one additional call out is keep in mind is common media client data spec. As that gets implemented in players and CDNs, that can really enhance this journey. We would have really kind of data-rich information, extra information coming in those requests from players onto the CDNs, and analyses like these, whether it's for monitoring, whether it's for quality of service investigation, whether it's for analysis like we've done here, could really be enriched by that implementation. So I want to thank you for the time. Thank you for listening. I hope you found this helpful. Thank you.